This episode is brought to you by Cisco Educational Premium. Do you know that equations of motion describe the behavior of a physical system? In physics, equation of motion describe the behavior of a physical system in terms of its motion as a function of time. The functions are defined in a Euclidean space in classical mechanics, but are replaced by curved spaces in relativity. Did you know that the first equation of motion is v is equal to u plus at? How do we derive this equation? When we rearrange the equation for acceleration a is equal to v minus u on t, and then we make v the subject of the formula, we get v is equal to u plus at, our equation of motion. Did you know that we can derive the first equation of motion using calculus? We know that the formula for acceleration is a dv dt. So rearranging this, we get a dt is equal to dv. Then after integrating both sides, we get integral from 0 to t a dt is equivalent to integral from u to v dv, which equals at is equal to u is equal to v minus u. Then rearranging, we get our first equation of motion, v is equal to u plus at. Did you know that we can derive the first equation of motion by graphical method? Say we have the velocity time graph for a moving object with initial velocity u and final velocity v, and the acceleration a as shown. From our graph, the velocity of a body changes from a to b in time t at a uniform rate. We can also see that bc is the final velocity and oc is the total time t. A perpendicular is drawn from b to oc. A parallel line is drawn from a to d, and another perpendicular is drawn from b to oe, as shown by the dotted lines, those dotted lines. We can see that initial velocity u is equivalent to oa and the final velocity v is equivalent to bc. Also, bc is equivalent to bd plus oc. Therefore, v is equal to bd plus dc, and also v is equal to bd plus oa, since of course dc is equivalent to oa. And so we have v to be equivalent to bd plus u, since oa is equivalent to u. Let us call this our equation 1. Since the slope of the velocity time graph is equal to the acceleration a, we have a to be equivalent to the slope of line AB, which is equivalent to BD on AD. And so since AD is equivalent to AC is equivalent to T, the above equation becomes BD, which is equivalent to AT. Let us call this our equation 2, shall we? Now, finally combining those two equations, we get V is equivalent to U plus AT, which is our first equation of motion. Did you know the second equation of motion is S is equal to UT plus half AT square? How do we derive this? From the first equation of motion, V is equal to U plus AT. We know that S is U plus V on 2 times T for linear systems where velocity is not constant. Then substituting the value of V from the first equation of motion, we get S is equivalent to U to bracket U plus AT bracket, then close the bigger bracket on 2 times T, which is equivalent to 2U plus AT times T on 2, which is also equivalent to 2U on 2 plus AT on 2 times T, which is equivalent to bracket U plus half AT bracket times T, Making further simplification and cleaning this, we get the equation S is equivalent to ut plus half at square. Did you know that we can derive the second equation of motion using calculus method? Mathematically, we can have velocity v to be ds on dt, and rearranging this we get ds is equivalent to v dt. Then substituting the first equation of motion to this we get ds is equivalent to bracket u plus at bracket dt, which is equivalent to bracket u plus at dt, which is equivalent to bracket u dt plus at dt bracket. Integrating both sides, we get integral from 0 to s ds is equivalent to integral from 0 to 2 u dt plus integral from 0 to t at dt is equivalent to s is equal to ut plus half at square. Our second equation of motion. Did you know that we can derive the second equation using graphical method? Say we have the velocity term graph as shown there. Using our graph, we can do some deductions. Distance traveled S is equivalent to the area of the figure OABC, which is equivalent to the area of rectangle OADC plus the area of the triangle ABD. And so, S is equivalent to half times AD times BD plus OA plus bracket OA plus OC bracket. Since OA is equivalent to U and OC is equivalent to T, we get this equation as S is equivalent to bracket half times AD times BD bracket plus bracket U times T bracket. We know that the BD is equivalent to AT, so the equation becomes S is equivalent to half times T times AT plus UT. And doing some simplification and cleanup, we get our second equation of motion S is equivalent to ut plus half at square. Did you know that that equation of motion is v square plus u square plus 2as? We can derive this equation by algebraic method. Mathematically, we know that displacement is equivalent to initial velocity plus final velocity on 2. So we have S is equivalent to u plus v on 2 times t. From the first equation of motion, we have v is equivalent to u plus at. So rearranging the above formula, we get t is equivalent to v minus u on a. Now, substituting t in the displacement formula, we get s is equivalent to v plus u on 2, v plus u on a, is equivalent to v square minus u square on 2a. So then we get 2as is equivalent to v square minus u square. And rearranging and doing some cleanup, we get v square is equivalent to u square plus 2as. Did you know that the third equation of motion can be derived from calculus? We know that acceleration is the rate of change in velocity and can be written as a is equivalent to dv dt. Let us call this our equation 1. We also know that velocity is the rate of change of displacement and can be expressed as v is equivalent to ds on dt. Let us call this our equation 2. So it follows that we cross multiply our two equations. We get a ds on dt is equivalent to v dv on dt. And so integrating from 0 to s a ds, it will be equivalent to integral from u to v dv. We will obtain the result as v square minus u on 2. Then doing some rearrangement, we get v square is equivalent to u square plus 2as. Our third equation of motion, by the way. At times you are getting an answer and you already forgotten the question. Did you know that we can derive the third equation of motion by a graphical method? Take a look at the velocity time graph. Our graph has all the information we require. And so we know that the total distance traveled S is given by the area of the trapezium OABZ. Therefore, S is equivalent to half sum of parallel sides times height, which is equivalent to half times bracket OA plus CB bracket times OC. Since we know that OA is equivalent to U, CB is equivalent to V, and OC is equivalent to T, the equation thus become S is equivalent to half times bracket U plus V times T, and since T is equivalent to bracket V minus U on A, the above equation can be written as S is equivalent to half times bracket V plus U bracket times bracket V minus U on A, which is equivalent to V square minus U square on 2A. Then engaging the brain just a little bit and solving this, we get our third equation of motion. V square is equivalent to U square plus 2AS. This episode is brought to you by Cisco Educational Premium. Did you know that Lippmann-Schrödinger equation is consistent with Schrödinger equation? The Lippmann-Schrödinger equation is one of the most used equations to describe particle collisions, or more precisely scattering in quantum mechanics. It may be used in scattering of molecules, atoms, neutrons, photons, or any other particles, and is important mainly in atomic, molecular, and optical physics, nuclear physics, and particle physics, but also for seismic scattering problems in geophysics. It relates the scattering wave function with the interaction that produces the scattering potential, and therefore allows calculation of the relevant experimental parameters, scattering amplitude and cross sections. The most fundamental equation to describe any quantum phenomenon, including scattering, is the Schrödinger equation. In physical problems, this differential equation must be solved with the input of an additional set of initial or boundary conditions for the specific physical system studied. The Lippmann-Schrödinger equation is equivalent to the Schrödinger equation plus the typical boundary conditions for scattering problems. In order to embed the boundary conditions, the Lippmann-Schrödinger equation must be written as an integral equation. For scattering problems, the Lippmann-Schrödinger equation is often more convenient than the original Schrödinger equation. The Lippmann-Schrödinger equation is useful in a very lineup of situations involving two-body scattering. For three or more colliding bodies, it does not work well because of the mathematical limitations. For diff equations may be used instead. However, there are approximations that can reduce a many-body problem to a two-body problems to a set of two-body problems in a variety of cases. For example, in a collision between electrons and molecules, there may be tens or hundreds of particles involved, but the phenomenon may be reduced to a two-body problem by describing all the molecule constituent particle potential together with the pseudo-potential. In these cases, the Lippmann-Schrödinger equations may be used. Of course, the main motivation of these approaches are also the possibility of doing the calculation with much lower computational efforts. From the mathematical point of view, the Lippmann-Schrödinger equation in coordinate representation is an integral equation of Fredholm type. It can be solved by discretization. This is equivalent to the differential time-independent Schrödinger equation with appropriate boundary conditions. It can also be solved by numerical methods for differential equations. In the case of the spherically symmetric potential V, It is usually solved by partial wave analysis. For high energies or weak potential, it can be solved perturbatively by means of bond series. The method convenient also in the case of many body physics, like in description of atomic, nuclear, or molecular collisions, is the method of the R matrix or Wigner and Eisenberg. Another class of methods is based on separable, separable, separable expansion of the potential of green operator, like the method of continued fractions of Harak and Sasakawa. Very important class of methods is based on variational principles. For example, the Schwinger-Langossos method combining the variational principle of Schwinger with Langossos algorithm. In the S matrix formulation of particle physics, which was pioneered by John Agbiwald Wheeler, among others, all physical processes are modeled according to the following paradigm. One begins with a non-interacting multiparticle state in the distant past. Non-interacting does not mean that all of the forces have been turned off, in which case, for example, protons will fall apart, but rather that there exists an interaction-free Hamiltonian H0 for which the bound states have the same energy level spectrum as the actual Hamiltonian. This initial state is referred to as the in state. Intuitively, it consists of elementary particles or bound states that are sufficiently well separated that their interaction with each other are ignored. The idea is that whatever physical process one is trying to study may be modeled as scattering process of these well separated bound states. This process is described by the full Hamiltonian, but once it's over, all of the new elementary particles and then a new bound states separate again, and one finds a new non-interacting state called the out state. The S matrix is more symmetric under relativity than the Hamiltonian because it does not require a choice of time slices to define. This paradigm allows one to calculate the probabilities of all the processes that we have observed in 70 years of particle collider experiments with remarkable accuracy. But many interesting physical phenomena do not obviously fit into this paradigm. For example, if one wishes to consider the dynamics inside of a neutron star, sometimes one wants to know more than what it will finally decay into. In other words, one may be interested in measurements that are not in the asymptotic future. Sometimes an asymptotic past or future is not even available. For example, it is very possible that there is no past before the Big Bang. In 1960s, the S-matrix paradigm was elevated by many physicists to a fundamental law of nature. In S-matrix theory, it was stated that any quantity that one could measure should be found in the S-matrix for some process. This idea was inspired by the physical interpretation that S-matrix techniques could give to Feynman diagram restricted to the Mars shell and led to the construction of dual-resonant models. But it was very controversial because it denied the validity of quantum field theory based on local fields and Hamiltonians. Intuitively, the slightly deformed eigenfunctions of the full Hamiltonian and in and out states, the phi, are non-interacting states that resemble the in and out states in the infinite past and infinite future. This intuitive picture is not quite right because psi is an eigenfunction of the Hamiltonian. Psi raised to plus or minus is an eigenfunction of the Hamiltonian, and so at different times only differs by a phase. Thus, in particular, the physical state does not evolve, and so it cannot become non-interacting. This problem is easily circumvented by assembling psi raised to plus or minus and phi into wave packets with some distribution Ge of energies E over characteristic scale delta E. The uncertainty principle now allows the interactions of the asymptotic states to occur over a time scale reduced Planck constant on delta E. And in particular, it is no longer inconceivable that the interactions may turn off outside this interval. The following argument suggests that this is indeed the case. Plug the Schrödinger equation into the definitions. Psi g raised to plus or minus t is equivalent to integral of dE e negative I et ge psi raised to plus or minus and psi gt is equivalent to integral dE e raised to negative I et g e phi of the wave packets. We see that at a given time, the difference between psi gt and phi gt wave packets is given by an integral over the energy E. This integral may be evaluated by defining the wave function over the complex E plane and closing the E contour using a semicircle on which the wave functions vanish. The integral over the closed contour may be evaluated using the Cauchy integral theorem, a search of the residues at various poles. We will now argue that the residues of psi raised to plus or minus approach those of phi at time t approaching positive or negative infinity, and so the corresponding wave packets are equal at temporal infinity. In fact, for very positive terms t and e raised to negative iet factor in a Schrödinger picture state forces one to close the contour on the lower half plane. The pole in the phi psi from the Schrödinger equation reflects the time uncertainty of the interaction, while that in the wave packets weight functions reflect the duration of the interaction. Both of these varieties of poles occur at finite imaginary energies and so are suppressed at very large terms. The pole in the energy difference in the denominator is on the upper half plane in the case of psi, and so does not lie inside the integral contour and does not contribute to the psi integral. The remainder is equal to the phi wave packet. Thus, at very late terms, psi will be equivalent to phi, and identifying psi as the asymptotic non-interacting out state. Similarly, one may integrate the wave packet corresponding with the psi, this one raised to a positive, this term, at very negative terms. In this case, the contour needs to be closed over the upper half plane, which therefore misses the energy pole of psi, which is the lower half plane. One then finds that the psi and the phi wave packets are equal in asymptotic past, identifying psi as the asymptotic non-interacting in state. This identification of the psi's as asymptotic states is the justification of the plus or minus epsilon in the denominator of the Schrödinger equations. The S matrix is defined to be the inner product. SAB is equivalent to psi raised to negative a plus psi raised to positive b, of the earth and bith of the earth and bith Heisenberg picture asymptotic states. One may obtain a formula relating the S matrix to the potential V using the above contour integral strategy, but this time switching the roles of positive psi and negative psi. As a result, the contour now pick up the energy pole. This can be related to the phi's if one uses the S matrix to swap the two sides. Identifying the coefficients of the size on both sides of the equation, one finds the desired formula relating to the S potential. In the Born approximation, the corresponding to the first order perturbation theory, one replaces this last psi with the corresponding eigenfunction phi of the free Hamiltonian, yielding SAB is equivalent to sigma A minus B minus 2I pi sigma EA minus EB phi A V phi B, which expresses the S matrix entirely in terms of V and free Hamiltonian eigenfunctions. These formulas may in turn be used to calculate the reaction rate of the process B as it approaches A, which is equal to SAB minus sigma AB squared. With the use of the Green's function, the Lippmann-Schrödinger equation has counterparts in homogenization theory, like mechanics, conductivity, and permittivity. This episode is brought to you by Cisco Educational Premium. Did you know that Schrödinger equation is a partial differential equation? Schrödinger equation tells us everything we need to know about a quantum system. The Newton's equation F is equal to ma tells us everything we need to know about the macro world around us, while the Schrödinger equation tells us everything we need to know about the quantum micro world below. Schrödinger equation governs the wave function of a quantum mechanical system. It gives the evolution of a wave function which describes an isolated quantum mechanical system. Schrödinger equation was postulated in 1925. It was postulated by Erwin Schrödinger. Erwin used William Rowan's Hamilton analogy between mechanics and optics to formulate it, but it was only good for describing quantum mechanical system. He wasn't sure with its meaning. Quite pragmatic, such a stereotype scientist. He published it in 1926 and was awarded the 1933 Nobel Prize in Physics. Schrödinger equation is analogous to the classical energy equation. Energy equation we are talking about here is energy is equivalent to kinetic energy plus potential energy. Schrödinger equation is I reduce Planck's constant H partial on partial T, the pitchfork which is called psi bracket x comma t bracket is equivalent to square brackets negative reduce Planck's constant square on 2m partial square on partial x square plus capital V bracket x comma t bracket closing the square brackets psi bracket x comma t bracket. So we have this first part representing energy, referring to the classical energy equation. Second part representing kinetic energy, and the third section representing potential energy. In Schrödinger equation, psi bracket x comma t bracket is a wave function. This is what we call a complex wave function. M is the mass of our quantum particle. Vxt, on the other hand, is the potential that represents the environment in which the particle exists. Constant I is the imaginary unit, and h is the reduced Planck's constant. Schrödinger's equation is a linear differential equation. This means that if two state vectors psi1 and psi2 are solutions, so are the linear combination psi is equivalent to a psi1 plus b psi2 of the two, where a and b are complex numbers. It's worth noting that this mathematical possibility allows for physical property of superposition of quantum states. Schrödinger equation can be applied to hydrogen atom. Schrödinger equation will evolve to E psi is equal to negative h, which is reduced Planck's constant square, on 2 mu delta square psi minus q square on 4 pi epsilon naught r psi, where q is the electron charge, r is the position of the electron relative to the nucleus, r is equivalent to magnitude of r, or vector r is the magnitude of the relative position. Potential term is due to the Coulomb interaction. Epsilon naught is the permittivity of free space, and mu is equivalent to mp on mq plus mp is the two-body reduced mass of the hydrogen nucleus of mass mp and electron mass m. C-square educational premium is a section of C-square educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of C-square educationals.
Yeah.